This lesson is an interesting one because it's truly just a skills-based lesson. You're going to learn a specific particular skill, but we're not going to really do many applications with it. We'll save our applications for later. So that means, AKA, like hardly any word problems, just a straightforward skill that you're going to practice. All right, the skill is called implicit differentiation. So let me kind of set that up for you. You can't learn this skill until you've learned the chain rule. So that's why we saved it for right now, for this lesson right now, because now that you have sort of mastered the chain rule, you'll be able to build on that and learn this next technique called implicit differentiation. All right, so one other review thing we want to set up is just some notation on how to write this correctly. All right, so we've learned that the derivative of the variable y with respect to the independent variable x, we wrote in Leibniz's notation as dy dx, okay? So then the derivative of y to the third with respect to the variable x, okay? The implied part of this problem is that there are parentheses around y, okay? So that y is the quantity that's being cubed. So when we take the derivative of this, we do this with the chain rule because we have parentheses. Anytime you have parentheses, implied or not, whether they're written in the problem or implied in the problem, you're going to use your chain rule. So the rule would be, okay, we'll pull our 3 to the front, we'll subtract our 1, and then we'll take the derivative of what's inside. Okay, so this is going to look like this. We're going to have 3. We're going to have y in the parentheses, and we decrease the power to 2, but it doesn't stop there. Because of the implied parentheses, we also take the derivative of what's on the inside, and the derivative of what's on the inside is dy dx. So you got to be comfortable with the implied parentheses around variables in these problems, okay, that you are additionally taking the derivative using the chain rule of what's left inside those parentheses. So let's see that in a couple other places. So if we have the derivative of b with respect to x, then that's written db over dx. But if we have the derivative of b cubed, we understand that there are parentheses implied there. So we're going to have 3 parentheses, b squared, and then times db dx as our derivative. The derivative of x with respect to x is dx over dx, which is the only reducible differentials there, so that reduces to 1. That's why the derivative of x is numerically 1. That's why we've been writing 1. But it's because dx over dx reduces. When we have x cubed, there is the implied parentheses. So our derivative would be 3 parentheses x quantity squared. And then dx dx is the implied derivative. We've been writing that as 3x squared, which is what it comes out to be. But it was before it was 3x squared, there was this implied dx dx there. So when we have x's as our variable, so when it's x with respect to x, that will reduce to 1. But when it's any other variable, b's, y's, w's, any other variable, you're going to have this extra db dx because of the chain rule. Okay, that's just notation. All right, so let's move on to your skill for the day. So far, everything you've done has been an explicitly defined function. Okay, what does explicitly defined function mean? It means that the function starts with y equals, and then we have our function. So you can always get y alone. That's an explicitly defined function, okay? Y is always alone on one side. It will also pass the VLT. So everything we've done so far has passed the vertical line test, and it's been written as y equals sine of x, y equals the square root of something, y equals, everything has been y equals. Today you're going to learn the skill of how to do implicitly defined, and they're not functions anymore. We call them implicitly defined curves. So it's not a function anymore, okay? These fail the VLT, but you can still take their derivative. Even if they fail the VLT, there's still a way to take their derivative, which is exactly what you're going to be learning today. All right, so these cannot be conveniently solved for y. In other words, you can't get y alone. Or even if you could get y alone, it's so messy with so many embedded square roots and cube roots and whatever that it's really not worth your time to do it. All right, but you can still take the derivative. So that's what we're going to learn today. Here's an example of a curve that's implicitly defined. You can clearly see that this fails the VLT. There is no way for this curve to be written. Okay, let's look at what the curve is. Here it is. Okay, that's the equation for the curve. But we can't get y alone here very easily. All right, now I'm not saying it's not possible. It is possible to get y alone. You would need something called the cubic formula. We've already learned the quadratic, but you'd need the cubic formula, and it gets very, very, very messy. And so it's not worth your time. It's much, much easier to know how to take the derivative without having to get y alone. So let's compare and contrast the order in which you do things, okay? For an explicit defined derivative, okay, when we do that first, you solve for y. In other words, get y alone. And then you differentiate using all the rules that we have, okay? So we've got power, product, quotient, and now chain rule. Okay, so that's always the order. Step 1, get y alone. Step 2, apply the rules. With an implicitly defined derivative where it fails the VLT, you reverse the orders. So step 1 is you differentiate without getting y alone. You still use the rules. You're going to need the product rule, quotient rule, chain rule, but you're not going to get y alone. You're going to wait, and you're going to do that second. And instead of getting y alone, you're going to get dy dx alone instead. That's what solve for that means. So get dy dx alone. So you're just reversing the order in which you do things. You'll still end up with a derivative, but the order that you do it is different. And it makes the math a lot easier. So let's practice one of those. Oh, actually, let me give you kind of a way to help remember that. Here's sort of an acronym. I love acronyms. We're going to look at the first. We've got differentiate, collect, factor, and solve. DCFS. Okay, DCFS. D, differentiate both sides of the equation. Doesn't say anything about getting y alone because we're not going to do it. We differentiate first. C, we collect the terms together. Okay, these are when you work with like terms, you're going to collect like terms. F for factor out your dy dx, and then at the end we solve. And that'll be the last thing. So D, C, F, S, differentiate first, collect like terms, factor, and solve. Okay, now we're ready for an example. All right, here's an equation. Find this derivative. Okay, this function, or this equation is not a function. It fails the vertical line test. It's going to be a sideways parabola if you actually looked at the graph. Okay, that's not really relevant. You don't have to look at the graph, but it would fail. And so we're going to use the DCFS acronym to help us remember. D is differentiate. Before you differentiate, I would recommend that you insert parentheses where they are implied. Okay, there is implied parentheses here around this y, 3 parentheses y squared. You need these around any variable that's not x. There's also technically implied derivatives right there, and the power is 1, Just want to make sure that you know where the implied parentheses go, because those places are going to need the chain rule because they're a variable other than x. So we're going to do the chain rule on both of those. All right, so differentiate first. So use the chain rule, which says pull the 2 down to the front. So this is where we saw earlier in our notation. So that will become 6 parentheses y. The new power is to the first, and then using what's inside the parentheses, there's an additional dy dx. So keep that straight. All right, plus. Now we're going to pull this power to the front. Okay, so I pull that 1 down, that's still a 2. The parentheses are there. When I decrease the power, okay, my power was 1, I'm subtracting 1, my new power is 0. And I have to remember dy dx on that as well. All right, what about the other side? Okay, we can think of our x as the same way, that it has implied parentheses there, and the 1 is going to come down to the front, which will give me 5 parentheses on x to the power 0, and then times dx dx as that variable. Okay, these are the derivatives. So it's a chain rule followed by multiplying by the derivative of what's in the chain rule. Now we can clean all this up. Okay, we can make this look a lot nicer. So this would be 6y dy dx. Plus, now we know that y to the 0 is 1. So this will become just 2 times dy dx. And on the other side, we know that x to the 0 is 1, and so's dx dx is 1. So we're left with equal to 5. All right, that's the differentiate step. Okay, D for differentiate. C is for collect. Collect being collecting the like terms. All right, well, what like terms are we talking about? We're talking about these derivatives here. These are the like terms. And this question already has them collected on the same side. Collecting means make sure that you've gathered all the dy dx terms on the same side as the equal sign. And we already have that here on this for this problem. So our collect part is done. Now we move on to factor. So because it has dy dx in common, we factor out dy dx. That will leave me with 6y plus 2, and then 5 is left by itself on the other side. So now I've factored. That's the F. And then the S is solve. Solve means solve for dy dx and get dy dx alone. And in order to do that, we divide. So dy dx by itself is going to be 5 divided by the quantity 6y plus 2. You don't have to write it with parentheses. You could just leave it as 6y divided by 2, but that's the derivative now, so we've done the solve. And we've done what the question asked us to do. The original question was find dy dx. Well, we've found dy dx. dy dx is equal to 5 divided by 6y plus 2. And remember, what this derivative tells us is it tells us the slope anywhere on the curve, even though it fails the vertical line test. Okay, so anywhere on the curve now, we can stop and find the slope, even if this curve failed the vertical line test. We would know what the slope was. Okay, D, C, F, S. All right, let's try another one. What is the slope of the line tangent to this? It looks horrendous, okay? It's a horrendous looking curve. It's really not that bad. Okay, but what is the tangent, the slope of the line tangent to the curve, that curve 2x squared at the point 3, 2? All right, we'll apply, because this fails the vertical line test again, we'll apply the DC of S rule. Okay, so we want to do, and it's also going to be helpful to us until you get good at this, as you're starting, be aware, okay, where all of your parentheses are. And you've got, it's like this. Those are all the parentheses. Around every variable, there is an implied set of parentheses. Okay, now let's do our differentiate. So pulling the 2 power to the front, subtracting 1, and remembering the chain rule. So we will have 4. The parentheses will be x to the first, and the chain rule will be dx dx. So until you get really good at this, I wouldn't suggest skipping any steps. I wouldn't suggest reducing that to 1 right away until you have gotten more comfortable with this. Don't skip steps. Okay, we'll pull our power rule to the front, we'll subtract 1, and we'll remember the chain rule. So that's going to give me 6 parentheses y to the first, and then times that chain rule. Equals. The next one is going to require me to do the product rule, because this is a multiplication. So it's not the power rule anymore, it's the product rule. And because 2 is a constant, 2 sits outside, and now I'm ready to do the product rule. The product rule says start with y, start with the second one, multiplying it by the derivative of the next, which is dx dx. And again, like I said, I know that's going to reduce to 1, but try to resist the temptation to do that right away until you've perfected this skill a little bit more. Plus, and then x, and then times the derivative of y, dy dx. And then minus the derivative of 6, which is the constant 0. Okay, that's the derivative. Once you have that derivative set, then you can go back and take and simplify everything, okay? So this is going to simplify to 1. This will simplify to 1, but nothing else does. So let's look at what we have here. We've got 4x minus 6y times dy dx equals, do your distributing here. So we'll have 2y, and then we'll have plus 2x, also with a dy dx on it. All right, this has all been part of the differentiate step. Now we're ready to collect. Okay, the collect part is to collect the like terms. And the like terms are this dy dx along with that dy dx. So we want to gather them together on the same side of the equation. And then what's the not like term, that would be this one, we want to move it over to the other side. So we're just doing algebraic movement here to collect these things together. So what I would suggest we do is that we subtract this 2x dy dx term over to the other side. All right, that's what I'm going to work on right now. So I'm going to work on that subtraction. So what I'll end up with is a subtracted 2x times dy dx followed by the 6y dy dx. And then the 4x I'm going to kick over to the other side. So I'll have 2y minus 4x. So now I've done the collection part, collecting those terms together. Now we factor, and we factor at what they have in common. So I notice that we have these like terms in common, but we also have a negative in common, and we have the number 2 in common. So I would factor out a negative 2 dy dx. And that's going to leave me with a positive x and a positive 3y. And then I'm equal to 2y minus 4x. That's the factor step. The last step would be solve, and we want to get dy dx alone. So dy dx will turn out to be the quantity 2y minus 4x divided by the negative 2 and the quantity x plus 3y. Okay, that is now my derivative. I found the derivative. It's using multiple variables. It has x's and y's in it, but I followed the DCFS rule for implicit differentiation. Now I can answer the question, which is, what is the slope at the point 3, 2? And so I can continue and I can plug in the values of 3 and 2 for x and y. So that'll be 2 times 2 minus 4 times 3 over negative 2 times the quantity, 3 plus 3 times 2. So this looks like 4 minus 12 over negative 2 times 9. So we have negative 8 over negative 18, which reduces to positive 4/9. So the slope I'm looking for along this implicit curve at the point 3, 2 is 4/9. Okay, this is our last one. Find the equation of the normal line. Okay, and to that implicit function, so again, a curve that fails the VLT, and we've been given our point. All right, so we have our point right here, but we need to find our slope. That'll be the next part. And so we want to follow, because this doesn't pass the vertical line test, the DCFS. All right, so let's put the parentheses in where they are implied. There are implied parentheses around the x, around both the x and the y, and around our y. So my rule here will be the power rule. My rule on the 2, the y squared will be the power rule, and this one is going to be the product rule. Okay, so step D, differentiate. 2 parentheses, x to the first times dx dx. That's my power rule with my chain rule for the parentheses. Minus parentheses, the product rule, which starts with y and then has dx dx on it. And then I add x times dy dx. Plus the power rule applied, so 2 parentheses y to the first times the chain rule dy dx. I tell ya, that chain rule is one that catches people over and over and over again. It's such a small rule, but it has big implications if you forget it. So train yourself to remember that. And then equals, and then the derivative of 7 is 0. So we want to simplify and clean this up. Dx dx will be 1 here. Dx dx will be 1 here. But I do have a negative to distribute. So I'm going to have 2x minus y minus x times dy dx, and then plus 2y times dy dx equals to 0. So my derivative step is done. Now I'll collect the like terms by kicking anything over to the other side that doesn't have the like terms in it. So remember, my like terms are the dy dx terms here and here. So I'll keep those where they're at. So negative x dy dx plus 2y dy dx, but to the other side, I'm going to kick negative 2x and a positive y. So my collecting of like terms is done. Then I factor. So I'll factor the terms that have the dy dx in common, which is all they have in common, leaving me with negative x plus 2y being equal to negative 2x plus y. And then solve. Then getting dy dx alone, which will have a numerator of negative 2x plus y and a denominator of negative x plus 2y. And my solving step is done. Now I need to figure out what the slope is going to be, so I'll use the point that I was given. So negative 2 times the x value of negative 1 plus the y value of 2 over negative quantity negative 1 for my x value plus 2 times 2. So that's going to give me 2 plus 2. It's going to give me 1 plus 4. So I'm looking at a slope value of 4 fifths. And then I just need to answer the question, which is the equation of the normal line. So I'll use point slope to answer the final values of the question. So I'll have y, the normal line, will turn out to be y minus the y value of 2, the normal slope of negative 5/4, and then x plus 1. And that's the equivalent value of your normal line. All right, so I hope that leaves you with a good starting point, a good sense of how to move forward with the implicit differentiation. And then you'll work on this through the exercises of your homework to practice this skill. All right, thanks, and yeah, good luck with this lesson.